Welcome to our new unit on chemical reactions. It's one of the best. In this unit, we'll look at balancing equations. We'll look at what reactants are, what products are. We'll look at different kinds of equations, different kinds of reactions, how to predict products of different reactions. It's pretty impressive. We'll start out with the basics. In a chemical equation, we have reactants and we have products. Reactants are what you start with, and products are what you end with. Products are what are formed. In a chemical equation, the reactants are typically written on the left, and the products are written on the right. In the middle, you'll find an arrow. Now, if I'm reading a description of a chemical reaction, I might see it written as like iron metal reacts with oxygen gas to produce iron 3 oxide. And that kind of tells me what the products are going to be. And they might use the word yields or gives to indicate the difference between the reactants and the products. But typically they're set up like this: reactants on the left, products on the right. The arrow points toward the products. Now, it doesn't matter how many reactants and how many products. Here's just kind of a generic reaction for the formation of bread. If bread is our product, we need flour, eggs, milk, salt, baking powder, oil, and all of it reacts together to produce bread. We may have reactions that are pretty complicated, and there's lots of reactants that all join up to make one big product. Sometimes we have one big reactant that might decompose or break down to give us multiple products. It doesn't matter how many reactants or how many products we have. Now, there are different ways of showing a reaction. Sometimes we write out chemical reactions as just words. We might have a word equation, or maybe here's the formation of water, or we would just write hydrogen reacts with oxygen to produce water. Hydrogen and oxygen are my reactants, and water is my product, the arrow pointing toward my product. Here we're going to start writing out formulas in our equations. We'll call this a skeleton equation. It's the same information. Hydrogen reacts with oxygen to produce water, but instead of writing out the words, we're going to use the formulas. Now, one thing we should make note of: there are certain elements that are found in pairs. Hydrogen and oxygen being an example. Back in the day, I think it was like September-ish, we mentioned this term diatomic. There are some elements on the periodic table that come in pairs. I'll get rid of this. We call them diatomic elements. Di meaning two, atomic atom. They look like this and this, where a hydrogen gas really is two atoms of hydrogen joined together. Oxygen in nature, elemental oxygen, comes in pairs. Now that we know a little bit more about bonding, it has to do with the way we can get stable, full outer shells, that each hydrogen really wants to share another electron. So being paired makes them much more stable than just individual hydrogen atoms. Kind of the same with oxygen gas. Each oxygen's got 6 valence electrons, and they end up sharing 2, so they get a total of 8. But they're much more stable when they're paired together, when they have their full octets, rather than just individual oxygen atoms. So we do need to become familiar with the elements that are diatomic. On the periodic table, they're hydrogen, way up in the left-hand corner, and then the rest of them are on the right-hand side. It's nitrogen, oxygen, and all the halogens: fluorine, chlorine, bromine, iodine, cysteine, and maybe we can leave it there. Tennessine, number 117, I guess would technically also be diatomic. But we won't deal with any element 117. So when these elements are in nature, not bonded with anything else, as elements, they come paired. So when I see hydrogen reacts with oxygen, and I want to write the formulas, hydrogen is H2 and oxygen is O2. And they join to form water, H2O. So sometimes we write out the reaction as words. Sometimes we write the reactions as the formulas, symbols. Sometimes we like to look at particle models. And then we can see that, oh yeah, that little subscript 2 means that there are 2 atoms of hydrogen. There are 2 atoms of oxygen joined together. H2O, I can see what a water molecule looks like. It's 1 oxygen with 2 hydrogen. Sometimes you might even see little symbols that tell you the states of matter, like this little G for gas or L for liquid. Those are just giving you even more information on what this is going to look like. It's hydrogen gas and oxygen gas reacting to form liquid water. The beauty of a chemical change is that we form something that is totally different. When we join elements, we have a new formula. That new formula is going to have different properties than the original reactants. Now, if you jump ahead a little bit, we'll come back to number 3 in a minute. But if you jump ahead here, there's a chart that has all kinds of symbols that we'll see in chemical equations. So we could see this plus, and that's showing us the different reactants and products. If there are multiple reactants and multiple products. The arrow means like yields or produces. It separates the reactants from the products. Now, the reactions that we deal with will only have a one-sided arrow. We will not deal with that reversible arrow, the third one down. There are some reactions that are reversible. They can go forward and make products. They can go backwards and reform the reactants. But we'll save that for a second year of chemistry. So we will not deal with this guy. But we'll definitely see the symbols solid, liquid, gas. They, again, just give us more information on what things are going to look like. S for solid, L for liquid, and G for gas. We're definitely going to see this word AQ, aqueous. An aqueous solution means that a substance is dissolved in water. It's a little bit different than the L. When you see the L for liquid, it's something that occurs as liquid in nature. Like water, for example. Water might have that L. Now, technically, water might have all 3 of them. I could have water as a solid, which would be ice. I could have water as a liquid, or I could have water as a gas, like water vapor. But the L is actually one that we don't use all that often. It's for a substance that would naturally occur as a liquid. The AQ we definitely use a lot, but it's for something that is dissolved in water. It's something that doesn't naturally occur as a liquid, but I dissolved it in water. For example, we could have sodium chloride with a little solid behind it. And if I saw a chemical equation with this in it, I would know that I'm using solid salt. Or I could see NaCl with an AQ. That means it's a salt solution. It's sodium chloride that's been dissolved in water. I would never use this symbol, NaCl liquid. That one gets a sad face. No, sad face. Sodium chloride doesn't occur in nature as a liquid. It's never naturally occurring as a liquid. The only way I can make it appear as though it's in the liquid phase is by dissolving it in water. We might see a little arrow that has the word heat on the top, or a triangle. And that does just mean that I'm heating my reactants in order to form products. Or sometimes we might see an element symbol written above the arrow, and that indicates a catalyst. A catalyst being something that just speeds up a reaction. It's not really a reactant or a product. I'm just using it to speed up the reaction. We'll talk a lot more about catalysts later on. So all of these are symbols that we should definitely be familiar with, things that I will see as part of a chemical reaction. Now, if I go back to number 3, it wants me to write a skeleton equation for the reaction of iron and diatomic oxygen gas to form iron 3 oxide. Okay, so we kind of read through this description and we're trying to put together the reactants and the products. And let's see, I have iron, which is symbol Fe. Iron is not a diatomic element, so its symbol is just Fe. In nature, iron is a solid. It's reacting with diatomic oxygen gas. So diatomic just meaning 2 atoms. In nature, oxygen is one of these diatomics. And they're telling me that it is a gas. And then it says to form. Enter in my arrow. To form iron 3 oxide. Now, how nice, they're telling me the formula. This is rust. This is the equation for the reaction that occurs when your iron cars and nails react with oxygen in the air and rust. It is a solid. It's kind of that rusty colored solid. Here then is my equation. Now, you may have heard of something called balancing equations, and this equation is not balanced, meaning that there's not the same amount of iron and oxygen atoms on each side, but that's okay. A skeleton equation is just supposed to give us the reactants and the products. Awesome. Now this part about sketching a molecular model, we'll deal with that later. For now, we just want to be able to read through a description of a reaction and figure out the reactants and the products and write their formulas. And maybe even put in the little phase symbol, solid, liquid, gas. Now they do mention one other reaction kind of at the end here, this decomposition of hydrogen peroxide. Here's another good example of a skeleton equation. At the beginning here it says hydrogen peroxide breaks down into water and oxygen molecules through what is called a decomposition reaction. Decomposition just means to break down. And so yeah, if I read that sentence, hydrogen peroxide is this H2O2. It does naturally occur as a liquid. You might have it in your medicine cabinet. It breaks down, or it produces, it forms water, which is naturally a liquid, and oxygen molecules, oxygen being a diatomic gas. Now this reaction happens on its own in nature, but you can speed it up by using a catalyst. So they're saying potassium iodide is used as a catalyst. So here's an example of where you might see a symbol for a formula written above the arrow, and it is just telling you that this reaction is being sped up by the addition of a potassium iodide catalyst. It's not really a reactant or a product, it's just making the reaction go faster. It's adding a little energy to help the reaction go faster. And we will run this reaction in the lab. Multiple times we'll run this reaction to kind of prove that there's water and oxygen gas formed. And you do not need to do question 4. We'll get into more specific details about catalysts in a later unit.